Okay, here we go. Section 5, more trigonometric equations. And as you can well imagine, if it's been split up into two different sections, this is the harder one. You can do this. We're going to split this up into two basic categories, solving these equations by using identities and looking at, what if it's not just x or theta? Multiples of angles. It's not really that hard as you might think right now. Solve the equation 1 plus sine of theta is equal to 2 cosine squared theta. Yeah, well, that whole factoring thing that we looked at in section 4 doesn't exactly work here because we have two different functions. But that's all right. We know that we could take cosine squared and do a substitution, one of our Pythagorean identities, and turn that into the sine function. So that's one of the first things that you're looking at here. Somehow transform the equation so you're only using one trigonometric function in the entire equation. So 1 plus sine of theta is equal to 2 times the quantity cosine squared is 1 minus sine squared. Do the distribution, don't get lazy. Now, if you look at this, again, like we saw in section 4, we've got a squared term. So this is in the form of a quadratic equation. In order to do that, we have our standard 5 steps. Step 1, we set it equal to 0. So again, we'll have to add 2 sine squared theta to both sides. And then we'll subtract 2, oh look, like terms. So we'll get 2 sine squared theta plus 1 sine to the first theta minus 1 equals 0. So again, putting them in descending order there of degree, getting it set equal to 0, that's step 1. Then we need to factor it. Well, okay, 2 is a prime number. The only way to factor down 2 sine squared, one of these is going to be 2 sine theta. The other one is going to be 1 sine theta. The negative here tells me my factors use opposite operations. So one is addition, one is subtraction. I don't know which is which. It does matter. And factors of 1. All right, so we do the FOIL method, or at least the two middle steps there. The outside product will give me negative 2 sine theta. The inside product plus 1 sine theta. That gives me negative 1 sine theta. Oops, I needed to have that positive. No big deal. Reverse the signs. Change the addition to subtraction. Now, here's a little tip. You don't have to erase the subtraction sign to turn it into an addition sign. You'd be surprised how many times I've seen people do that. So again, my outside product gives me plus 2 sine theta. The inside product minus 1 sine theta, giving me my middle term here. All right, so we set it equal to 0. We factored it, set each factor equal to 0. So 2 sine theta minus 1 equals 0, or sine theta plus 1 equals 0. Step 4, solve each of them individually. So over here, I'll have to add 1 to both sides. Divide by 2. And then our handy dandy note cards here. Sine is equal to 1/2 at pi over 6. Again, that's our first quadrant, but sine is also positive in the second quadrant. And if pi over 6 turns out to be our reference number, that means sine is 1/2 also at 5 pi over 6. Now again, I'm going to put that on pause for just a moment here. The way, again, your authors, the way we talked about it last time. We're going to go through and we're going to solve just for these values in one cycle. And then we'll turn it into expressions for all the solutions. One at a time here. Deal with the other factor. Now in this case, okay, sine is equal to -1. That happens only once between 0 and 2 pi. That happens at 3 pi over 2. So there are all the solutions within one period, within one cycle. So then we need to take this and this and turn it into our expressions here for all the solutions. So theta could be equal to pi over 6 plus 2k pi, or 5 pi over 6 plus 2k pi, or 3 pi over 2 plus 2k pi. All right, let's take a look at solve the equation cosine theta plus 1 is equal to sine theta in the interval from 0 to 2 pi. Okay, so first of all, here's our lovely equation. But now, very, very different here. We're not looking this time for an expression that covers all the possible solutions. We're just going to focus in on this interval. All right, now, again, careful about the symbols there. The squared off bracket with the 0 means it can be equal to. The curved parentheses there with the 2 pi means it's equal to 0 up to, but not including 2 pi. Okay, so with our lovely equation here, cosine theta plus 1 is equal to sine theta. So what kinds of there's nothing really that jumps out there, is it? You know, if that said sine squared, we could do something with that. Or if that said cosine squared, we could do something with that. But the fact that at this point in time, yeah, there are no substitutions that work. Sometimes you're going to have to get creative. Let's square both sides of the equation. Now here on the left, again, it's a binomial that we're squaring. That means multiplying it by itself. And hopefully your algebra skills are still strong enough to know outside product will give us cosine squared. In the FOIL method here, the outside is going to be 1 times cosine theta. The inside product, cosine theta times 1. All right, so that gives us 2 cosine theta. And 1 times 1, hopefully, is 1. And here, the much simpler sine squared. Now we're back to the issue that we saw from the previous problem there. Yay, we have an equation with two different functions. Let's use our standard trigonometric substitution here. So we're going to leave this as cosine squared theta plus 2 cosine theta plus 1. Sine squared is 1 minus cosine squared. Combine like terms, we'll add cosine squared to both sides. No, they don't cancel. I see that mistake so often because people just decide to get a little lazy. Oh, here we got one on this side and a negative on that side. They cancel. No, they don't. Subtract one. Now those. All right, so this gives us 2 cosine squared theta plus 2 cosine theta is now equal to 0. Hopefully the factoring, since there are only 2 terms on the left-hand side, isn't all that challenging. 2 is a common factor, and cosine theta is a common factor. Factoring is division. 2 cosine squared divided by cosine, that'll leave us with one of the cosines. 2 cosine theta divided by 2 cosine theta is 1. Again, we had 2 terms. We factor out the common factor. We still, inside the parentheses, have to have 2 terms. All right, so we set it equal to 0. We factored it, set each factor equal to 0. So 2 cosine theta is equal to 0, or cosine theta plus 1 is equal to 0. Do I really have to say divide both sides by 2? Cosine theta is equal to 0. Well, on your note card here, that happens when theta is pi over 2, goes down to its minimum, and then it happens again at 3 pi over 2. And those are the only solutions that are in the interval that they insisted upon. Okay? On the other side, I have to subtract 1 from both sides. So I'm looking for the values where cosine is negative 1. Well, again, in this interval, there's only one time that that happens, and that's at pi itself. When the directions restrict the interval, we don't have an infinite number of solutions. In this case, we have just those 3. But wait, isn't this supposed to be a 5-step process? We set it equal to 0. We factored it. We set each factor equal to 0. We've solved. What's this mysterious 5th step that you're talking about, Mr. Mark? We check. We have to go back. Sorry, let me clean this up a little bit here. We need to check each of those solutions. So we're going to take the cosine of pi over 2, add 1, and to see if that's equal to the sine of pi over 2. Well, for pi over 2, the cosine is 0. 0 plus 1 is 1. For the sine of pi over 2 is 1. That one checks out. For 3 pi over 2, we need to know cosine of 3 pi over 2 plus 1 to see if it's equal to the sine of 3 pi over 2. Well, the cosine of 3 pi over 2 is 0 plus 1. That'll give us 1. The sine of 3 pi over 2 is negative 1. Oops! that does not check out, we need to remove that one from our list of solutions. And then, does the cosine of pi plus 1 equal the sine of pi? So again, for cosine of pi is -1 plus 1, that should be 0. Sine of pi is 0, that one checks out. Okay, so be careful here when you're doing this. The very first thing we did was we fundamentally changed the equation. It starts off as first degree. We squared both sides. Sorry, the dog is very much enjoying the chew toy, if you can hear that noise in the background. We squared it. This is usually, I'm not going to say always, this usually results in what we call extraneous solutions. Because we're changing the degree of it, turning it into something that we can factor down, we're going to get extra solutions that do not meet the original equation. Okay? So please make sure that you're doing the critical fifth step and checking your answers. All right, for our next one, find the values for x for which the graphs of sine x and cosine x intersect. Now, the way they've written this here is, again, focusing on the graph. We'll need a graph. And again, with the graphing calculators, this is so simple to do. Now, again, we might be better off here if we zoom in on our trig function. Yeah, it's a video. You can go back and watch if you don't remember. You can rewind that part. Cosine. We do have points of intersection. We have a point of intersection here, and down here, and back here, and okay, so again, the directions are not restricting our domain or range this time. So we need to come up with an expression for all of these possible solutions. So again, your calculator's equipped, menu, analyze the graph. We're looking for the points of intersection. The lower bound, the upper bound, there's one of our points of intersection. And for the other one, analyze the intersection to the left and to the right. So then it's just a matter of, can we read those? Does that Y value look familiar? Does that sound familiar? I'm sorry, if I can move this. Move those labels out of the way. There, that's much easier to see. The X value is 0.785 when the Y value is 0.707. Now, if those values do not look familiar, that's all right. 0.785. So we can say here, X is approximately 785. Again, because of the repetition, plus 2k pi, or X is approximately 3.93 plus 2k pi. Now remember, we're looking for, again, just these two values between 0 and 2 pi, and then turn them into the expressions there for all multiples to the left and to the right. Now, another way of approaching this is algebraically. We're looking for the intersections here where sine x was equal to cosine x. I'm not going to get too fancy here. I don't want to square both sides like I did with that previous equation. If I just divide both sides by cosine, that's my definition of tangent. Where is tangent equal to 1? Well, then x is equal to, again, from your note card, pi over 4. Now again, a closer look at the note card there. If x is pi over 4, notice sine of pi over 4 is square root of 2 over 2. Cosine is square root of 2 over 2. They are equal to one another. Okay? Plus 2k pi. So how do we get the other one? We know tangent is positive in quadrant number 1. Okay, that's on your note card. But tangent is also positive in quadrant number 3. So again, the pi over 4 becomes our reference number. We want something in quadrant 3. It's basically going to be pi plus the pi over 4. So that'll give us 5 pi over 4 plus 2k pi. All right, next example, consider the equation 2 sine 3 theta minus 1 is equal to 0. And basically they're giving you both types of directions here. Find all the solutions and then list all of the solutions that are just in the interval between 0 and 2 pi. Well, all right, so 2 times the sine of, oh, okay, there's the difference. It's not just x, it's not just theta, it's 3 theta. How do we deal with that? We deal with it later. Do the algebra first. 2 sine 3 theta is equal to 1. Divide both sides by 2. So sine of 3 theta is equal to 1/2. And again, from our note card, we know that 1/2 happens for sine at pi over 6. In the first quadrant. And then in the second quadrant, again, pi over 6 is our reference number. So that turns out to be 5 pi over 6. Again, all the solutions. So we'll do our standard plus 2k pi. And then we realize that this isn't theta. That's 3 theta. We don't want to know. We're not trying to solve for 3 theta. We're trying to solve for theta. So what we need to do now is, okay, divide by 3. So now theta is equal to, okay, pi over 6 divided by 3. Dividing by 3 is the same thing as multiplying by 1/3. So 1 pi over 6 times 1 over 3 should give me pi over 18. And no, I really don't need a common denominator there. And then from the second one, this will be, again, divide by 3. So this turns out to be 5 pi over 18 plus 2k pi over 3. So those expressions are the solutions here for part A. Now, how do we deal with what they're asking you to do for part B? So again, here are the expressions that we just came up with. So let's list all of the possibilities here. Again, we've described this before. K has to be an integer. So if we substitute 0 in place of k, which basically makes that second part of it disappear, we'll get pi over 18. And the second one will get 5 pi over 18. But again, that's not everything between 0 and 2 pi, is it? What happens when k is equal to 1? Oh, yay, you guys love fractions, don't you? So this turns out to be 18 pi plus, well, if k is 1, that's, sorry, 2 pi over 3. Well, now we do need the common denominator. So that'll be 18. Of course, that means multiplying top and bottom here by 6. So that turns that into 12. 1 pi over 18 plus 2 pi over 18 will give me 13 pi over 18. Well, 13 pi over 18 is less than 1 pi. So I definitely need to keep going here. So I'll take 5 pi over 18. And you know it's going to turn out to be the same here. So this is going to be plus 12 pi over 18. So that gives us 17 pi over 18. Well, we're still not at our limit yet. Let's try when k is equal to 2. So this is going to be pi over 18 plus, well, 2 times 2, that'll be 4 pi over 3. Common denominators again. So 1 pi over 18 plus 24 pi over 18 will be 25 pi over 18, which then should have you scratching your head here. Wait a minute, if we've got 18 as the denominator, 2 pi, yes, is 36 pi over 18. So again, we need to keep going. 5 pi over 18 plus 24 pi over 18. That'll give us 29 pi over 18. What happens when k is equal to 3? So pi over 18 plus 2 times 3 would be 6 pi over 3. Oops, wait a minute, hold on. 6 pi over 3, that's equal to 2 pi. And if I add the pi over 18 plus 2 pi, I've gone too far. My list is finished. Okay, so again, so this is for part B where it says find the solutions in the interval from 0 to 2 pi. We have to find the solutions when k is equal to 0. Find the solutions when k is equal to 1. Find the solutions when k is equal to 2. But that's where we get to stop, because if k is equal to 3, we've gone too far. We're beyond what they asked us, the interval they asked us to use. All right, so let's try one more. Again, I'm sorry, let's back up and get a little perspective here. initially it's the same solution process. Okay. Use your algebra skills, isolate the variable term, isolate the variable itself. But in this case, because it's not just a single angle, it's not just x, it's not just theta, there's one additional step here in coming up with our solutions by getting it from 3 theta or 27 theta or 5x or whatever it is down to just the angle itself. Find all solutions. Ooh, find all solutions in the interval between 0 and 4 pi. Okay, that'll be interesting. All right, so I don't know, can I do the first step here? I'm just going to do it off to this side here. So square root of 3 times the tangent of theta divided by 2. I'm going to go ahead and add 1 to both sides is equal to 1. Then get rid of that coefficient by dividing both sides by square root of 3. So tangent of theta divided by 2 is 1 over square root of 3. Now again, some of you are screaming that that's not proper form here. Okay, fine. So we will transform that into simplest radical form, square root of 3 over 3. Well, we know, again, from your note card, that tangent is equal to square root of 3 over 3 when the angle is pi over 6. So we have, theta over 2 is equal to pi over 6. But unlike what we did with the last one here, this isn't a multiple of theta. This is a subdivision of theta. We have to multiply both sides by 2 to say then that theta is equal to 2 pi over 6 is the same thing as pi over 3. But I also have to include, all right, it's the tangent function that we're solving here. There should have been a plus k pi. Again, the normal period for sine and cosine is 2 pi. The normal period for tangent is only 1 pi. That should also be multiplied by 2. So in the end, we get a 2k pi. A quick look at the graph here. Again, I've graphed things a couple of steps into our solution process. So what you see here in black is the tangent of theta divided by 2, or x over 2. And then the nice horizontal pink line here is square root of 3 over 3. And you see here for one period where it goes all the negative values, goes through 0, 0, turns all the positive values here. There's only one point of intersection. Okay, so again, for this, we need just one expression there. That takes care of all of the different intervals. Okay, so again, this is our answer for part A. Part B then, well, when k is equal to 0, theta is equal to pi over 3. When k is equal to 1, we need to take pi over 3 plus, okay, k is 1, that becomes 2 pi. So that's pi over 3 plus 2 pi over 1, otherwise known as 6 pi over 3, plus 1 pi over 3. That'll give us 7 pi over 3. Now again, you're screaming, hey, wait a minute, we've gone past 2 pi. Note here, find the solutions in the interval here from 0 to 4 pi. This is legal. we can keep going. 1k is equal to 2. Well, 2 times 2, that's going to be taking pi over 3 plus 4 pi. Yep, that's too much. We've gone too far. Even stretching out that interval so it goes from 0 to 4 pi only yields 2 solutions. Okay, take a look, give it a shot, do your best, write out your work, write out the steps in your solutions. Don't do too much mentally here. Again, it's so easy to be concentrating, oh, what am I going to do with that sine function? What am I going to do with the tangent? That most points are lost here with simple algebra and arithmetic mistakes, not the trigonometry. Don't fall into the trap. Okay, good luck